intermediate value theorem says that if a function goes from one point to another, from f of a to f of b, then it must go through all the values in between, and here we're calling it k, is what this thing is saying, as long as the function's continuous. So, let's take a look at what this thing really means. Alright, so this theorem gives us two conditions here. If these two conditions are met, if the function's continuous on some interval a, b, and k is any number between f of a and f of b, then f of c equals k for some c between a and b. So this is a whole lot clearer when you can draw a picture. So let's say this is a and this is b. This is our closed interval from a to b, okay? That's what this says. And it says f of x is continuous from there. So it just goes from some point, like right here, and if this is a and our function's f of x, then the y value is just f of a. And let's say b is up, or the point for b is up here somewhere. So that makes this right here f of b. F of a is right here. Okay, so we're looking at the interval from a to b on the x-axis and from f of a to f of b on the y-axis. So our function's continuous there. So I'm just going to draw a continuous function. There you go. Who knows what it does outside that interval, but right there it looks at just a nice continuous function. And k can be any number between f of a and f of b. All that means is k is some number on this axis right here between f of a and f of b. Now, k is completely arbitrary as long as it's between a and b for this purpose of this example here. So I'm just going to say k is right here. So there's k. And all this theorem says is if there's a value between f of a and f of b, you should be able to find a point on that function where it equals that number. So they make it look a little bit more complicated. They say there's some value c. Let's make it a little bit bigger. Some value c. That looks hideous. Let's try that again, Mr. Smith. There we go. So there's some value c where if you take the function at c, you get k. For any value k you choose between f of a and f of b. That's it. And f of x can look like anything. F of x can be any kind of function you want. As long as it's continuous, you can see that it's going to eventually hit k right there. So that's all intermediate value theorem says. And what it's really saying here, so theorem is just a mathematical rule. That's what this is. It's a theorem. It's called intermediate value because we're talking about the values in between our y values that are endpoints. That's why it's called that. So it's the intermediate value is k because it's in between f of a and f of b. And it says if the function's continuous from here to here, then it must also hit k somewhere. So let's take a look at an example here, like a concrete example here of a function. So questions you'll see usually look like this. Determine if IVT can be used to prove f of x equals 3.5 on this interval. Well, to determine if we can use IVT, all that really means is are the conditions for IVT met? So let's go back to conditions for IVT. We need f to be continuous on the interval from a to b. Well, let's check this out here. We've got, well, that's example 2. Oh, let's see this guy. F of x is the square root of x plus 2. Well, this function's continuous as long as it's defined, and square root of x is defined everywhere x is greater than or equal to 0. And we're on the interval from 1 to 4, so this thing's defined everywhere, so it's also continuous. So that's what I'm going to write. Number 1, f of x is continuous on 1 to 4. Yeah, it's continuous because that's the square root function. And you can write that out if you want. Since the square root function, so let's do this. Since root x is continuous for all x greater than or equal, or greater than 0, I guess, not equal to 0. Okay, now you can plug in 0. That's what I'm saying. It's not continuous at 0 because it stops at 0, so there's no left side to that. So it's not continuous at 0. So the first condition's met. Since it's continuous for anything greater than 0, it must be continuous from 1 to 4. The second part is we have to check the endpoints and see is k between f of a and f of b. Well, k is 3.5, okay? Right there is k. That's the f of x equals 3.5. Cool. Now, they said, I said c in this theorem here, f of c equals k. They're saying f of x equals k. It doesn't matter. It's just a variable. So you can think of this as the f of c equals k is right there. Does my function have to equal 3.5? Well, I know it's continuous. Cool. Now it's going to find the endpoints. Well, f of 1 is equal to the square root of 1 plus 2. Well, that's 3. F of 2 is equal to the square root of, not 2, 4. f of 4 is equal to the square root of 4 plus 2. Well, that's 4. So my function's continuous, and the y values go from 3 to 4. And since it's continuous, then somewhere in between 1 and 4, my function must equal 3.5. And that's exactly what we're going to say as our answer to if IVT can be used. So we check the conditions. Number 1, it's continuous from 1 to 4. No problem. Number 2, the function goes from 3 to 4, and the k value we're interested in, 3.5, is in between there. So those are our two conditions. K is between f of a and f of b. F is continuous on the interval. So there must be some place where f of x equals k. So we're going to write that. Let me erase this here, and we'll just write it out. I'll show you what an answer would look like for IVT problem. Okay, let's get rid of all of this. You just write a little sentence explaining why this works. So, since the conditions are met, and that's what we just checked, the conditions are met, IVT applies, or holds. Sometimes they'll say it holds. Same thing. IVT applies here, and f of c or f of x, whatever. They say c to distinguish between that. It's not any x value. There's a particular value where it has to happen. But f of c has to equal 3.5 for some c on this interval. So somewhere between 1 and 4, there's a value I can plug into f, and I should get 3.5 back. Let's take a look at a picture of what this looks like. So, of course, that's not going to work. So that's what that looks like. And let's just draw a picture here and show you exactly what I'm talking about here. So IVT doesn't really say anything that's super incredible. It's actually fairly obvious. Okay. Now you don't have to draw a picture, but drawing a picture usually helps. So at 1, we said this thing was 3. The function value was 3 at 1. That's right here. And at 2, 3, 4, when you plug in 4, we get 2 plus 2, which was 4. So we know my function's continuous. I don't know exactly what it looks like. I mean, I might be doing all kinds of crazy stuff here. Cool. But I know it's continuous, so it has to connect these two dots like this somehow. Okay? And 3.5 is right here. Here's 3.5. And since it's continuous, there has to be some spot on my function that equals 3.5. That's all we're saying. It's pretty obvious to look at once you draw it. It goes from 3 to 4. So therefore, it must equal 3.5 because it's continuous. So 3.5 somewhere. If the question asks you to find out where it equals 3.5, well, then you just take your function and set it equal to that value. So if it says find the value where it happens, well, let's do this. So we'll solve for x. Minus 2, well, that's 1.5 is equal to the square root of x. And you square both sides. And if you square 1.5, you get 2.25 is x. So if x is 2.25, then I get f of 2.25 is 3.5. And you can see 2.25 is between 1 and 4. So let's check out another example. Example 2. Determine if IVT can be used to show that f of x equals 0 on the interval -2 to 3. All we're going to do, when you see determine if IVT, if IVT can be used, what you're going to do is check the conditions. So number 1, is f of x continuous? Well, look, this is a fraction, so we got to make sure we're not dividing by 0. And when x is 1, we get 1 over 0, and that's undefined, which means f is not continuous at 1. Since 1 is on the interval between -2 and 3, 1 is in there, IVT doesn't have to apply. The function does not have to equal 0 between -2 and 3 because the function's not continuous. That's all we need to check. Since f of x is not continuous at x equals 1 because f of 1 is undefined. Okay, you get 1 over 0, that's undefined. And 1 is on our interval. 1 is between -2 and 3. You can write that like this. 1 is in the interval. It's between -2 and 3. IVT does not apply. There you go. That's all you got to say. The conditions are not met, so IBT does not have to apply. And all we're saying is determine if it can be used. And well, no, IBT doesn't work. You can't use it unless these conditions are met. All right, last one. Last example. Determine if IBT can be used to prove f of x equals 2 from 1 to 3. Okay, no problem. Well, first off, we got to make sure that it's continuous on this interval. So 1 over x is not continuous when x is 0. But since 0 is not on this interval, we don't have to worry about that. It's continuous everywhere else. So we're going to write that. F of x is continuous for all real numbers except x equals 0. So, since 0 is not our interval, it must be continuous there, so it must be continuous. On the interval we're interested in, 1 to 3. Okay, so that holds. That step holds. It's continuous. Let's check the endpoints, too. F of 1 is 1, and f of 3 is 1/3. Okay, so our function goes from 1 to 1/3, and we're trying to show, can we use IVT to say that it must equal 2 somewhere? Well, since my function goes from 1 to 1/3, 2 is not in between those values. 2 is greater than both of those values. And that is a condition for IVT to work. K has to be between f of A and f of B. Well, in this case, K is 2. F of A is 1. F of B, which is 3, is 1/3. 2 is not between those values, so IVT does not apply. And that's all you're going to say. The function's continuous, so it has to equal any value between 1 and 1/3. That's true. However, 2 is not between 1 and 1/3. So we're just going to write that out. IVT does not apply because 2 is not between 1 and 1/3. We can write that with inequalities like this. 1/3 is less than 1, which is less than 2. 2 is not between them. So IVT does not apply. We cannot use it to say that it equals 2. Let's take a look at an example. I'm just winging this one here. Let's take an example of a function that we just looked at one where IVT did not have to apply. Okay, but let's take a look at an example where IVT isn't going to apply for this one. Let's say f of x equals x over x minus 1. All right, and let's say I want to know, can we use IVT? So let's type this out here. Can IVT be used to show that f of x has to equal 0 somewhere on the interval from, I don't know, -2 to 2. Okay. Now, I'm doing this for a reason here, but check this out. Can we use IVT to show that f of x equals 0 somewhere on -2 to 2? Well, if you take a look at our function, it's continuous everywhere except for where the denominator is 0, which is 1. So, IVT cannot be used. All right, let's get this clear. IVT cannot be used because f of x is not continuous. Continuous at x equals 1, and 1 is on the interval we're interested in, and 1 is between -2 and 2. Okay, so the reason I chose this example, got a speech problem here, is because IVT can't be used to say that it definitely has to equal 0, but it doesn't mean that the function doesn't equal 0. We just can't use IVT to say it. This function actually does equal 0 on this interval somewhere, but IVT can't be used to prove it. Okay, so that's a weird thing about IVT that I think kids don't understand a lot of times, or sorry, students, young adults. they don't understand that just because IVT can't be used, it doesn't prove that the function can't equal this value. Okay, it doesn't prove f of x does not equal 0. We just can't use f of x, or we can't use IVT to say that it does equal 0. So, for instance, this thing equals 0. This does equal 0 when x is 0. Okay, and 0 is on our interval. That actually works. 0 is on this interval here. Okay, so f of x equals 0 when x is 0, which is on this interval. The problem is it's not continuous the whole time on the interval, so we can't use IVT. So IVT is called an existence theorem because it says that if the conditions are met, then this point, f of z equals k, has to exist. It has to be there somewhere. It doesn't say what happens if these conditions aren't met. It doesn't say that this isn't going to happen. Okay? It doesn't tell us anything about that. It just says if the conditions are met, then the function has to equal any value in between the endpoints. But in this case, the conditions aren't met, but our function still equals the value we're interested in. So again, IVT does not say anything about what happens if the conditions are not met. It only says what happens if the conditions are met. That's an important thing to remember.